All right, what we're going to do now in section 6.5 is start graphing polar equations without the use of a calculator. We will use the calculator or maybe even the computer to help us explore some of these things, but what we'd like to do is get to a point where we can graph any of these without a calculator. So we're going to start out with something really simple, like r is equal to 3. The interesting thing about that is that it does not depend on the directed angle. So what this is basically telling us is that whatever angle we're at, we have to be 3 units from the pole. So if we start plotting a bunch of points that are exactly 3 units from the pole, what we get is we get a circle centered at the pole or origin with a radius of 3, and as you know, there's an infinite number of points that satisfy that condition. So there is an example of a polar graph. R is equal to 3. Next to that, we're going to graph a polar graph that has no specification for R. So R could be anything, but the directed angle has to be pi over 3. So this is the directed angle of pi over 3, if you remember from the polar axis. So any point along that line is going to be an angle, a directed angle of pi over 3. Now you might be asking, well, what about the ones on the other side of the pole? You could say that those are a directed angle of pi over 3, but their directed distances are negative. So theta equal pi over 3 forms a line along the directed angle of pi over 3. So those are kind of some simple ones. What we're going to do next is we're going to move on to graphing things like r is equal to cosine theta and r is equal to sine theta. And before we do that, we're going to do a quick review of graphing those two functions in the Cartesian system. So if you look at the graph in front of you, the cosine function is graphed in red. And let's just kind of go through and hit some highlights of that. So the cosine of 0 is 1. That's why we have a point right up there at x equals 0. And let's see, let's think of some other critical values. Well, the cosine of 90 is 0, so that point is right there. And the cosine of 180 is -1, so that point is located right down there at the bottom or the minimum value of the curve. And the cosine of 270 is 0 again, and when we get back around to 360 degrees, we're back at the maximum of 1. So we could do a similar thing with the sine function, but what we're going to do is we're going to move down here and we're going to keep in mind those critical values of the cosine function. For example, at 0 degrees, at 90 degrees, at 180 degrees, at 270 degrees. So we're going to move to our polar coordinate system right here. And at 0 degrees, we see that the cosine is at its maximum value of 1. So I'm going to treat this point out here as the maximum distance from the pole of 1. When I move to 90 degrees, it's back to 0. So that's going to put us right here at the pole. And when I move to 180 degrees, it's going to, r is going to be -1. So if I turn to 180 degrees directed angle and start to go 1 in that direction, I don't really want to do that. I want to go back to -1. So I have another point here that's coincident with the first point. And then at 270 degrees, we're going to be at 0, which is going to put us back at the pole. So what happens in between? Well, let's take a look at some points between x equals 0 and x equal 90 on the Cartesian graph above? Well, what we know is that as x goes from 0 to 90 degrees, y, or the cosine of x, is actually decreasing. So the R value is going to do the same thing, and what we can do is we could sort of graph some points. So if we graph a point that is 15 degrees from 0, we see that the y value, which now corresponds to the r value, is a little bit less than 1. And then 30 degrees, that's even a little bit less than 1. And 45 degrees, that's even a little bit less. And at 60 degrees, even a little bit less. And so what we see is that as we are rotating around here, our points are getting closer and closer to the pole. Now let's see what happens when we go from 90 degrees to 180 degrees. So at 90 degrees, we're at 0. At 90 plus 15, or 105 degrees, we have a negative value. So if we turn to 105 degrees and we go the opposite direction there, make sure I'm on the right place, I'm not exactly at 0, but I'm negative. And then if we add another 15 degrees to that, so 120 degrees, it looks like our y value up on the top is about -1/2, and that means we're going to be about halfway between the pole and the outer perimeter of our graph right here. And as we continue on, what we're going to see is we're getting closer and closer and closer to 1, or -1, excuse me. And if we start connecting those points, what we see is we see something that appears to be circular in nature. And I didn't do such a great job of graphing it there, but that's exactly what we have. Now, if we start to look at the critical values for the sine function, we're going to see a similar thing. So let me pause here. I'm going to switch colors and we'll get back to that. All right, so just like we did for the cosine function, we're going to do a similar thing with the sine function. We're going to start off with a quick review of one period of the sine function in a Cartesian coordinate system. So the critical values: at x equals 0 degrees, the sine of 0 is 0. At 90 degrees, the sine of 90 is 1. At 180 degrees, the sine is 0 again. And at 270 degrees, the sine is -1. And when we're back at 360, the sine is 0. So we're going to use those points to help us plot r equals sine theta. R is equal to sine theta. So we'll start at 0 degrees. At 0 degrees, we are at the pole because r is 0. At 90 degrees, we are the furthest distance from the pole. Remember, the outside perimeter of our graph is 1 unit away from the pole. At 180 degrees, we're back at 0. At 270 degrees, we're at -1. So we go to 270, but we don't go in that direction. We go the opposite direction. So there's a point right on top of the second point we plotted at 90 degrees. And at 360, we're back at 0. Well, we can do the same thing that we did with the cosine function with the sine function. So let's take a look at what happens to the sine function in the Cartesian coordinate system between 0 and 90 degrees. What we see is we see that the same way that the cosine function was decreasing on that interval, the sine function is increasing on that interval up to a maximum of 1. So as you can imagine, we start plotting points every 15 degrees, and we're going to get points that are getting further and further and further away from the pole. And if you follow this through, you can see that we get a graph that looks like that. When we get to 90, we're at the maximum distance from the pole of 1, and as we go onward, we can see that the points, as the angle increases, the points get closer and closer and closer to the pole, and what we have is we have another circle. What I'd like you to do right now is I'd like to put you to put your calculator in polar mode if it's not already, and graph these functions right here that I am drawing a box around, and do one at a time, and then answer the questions below. So now that you had a chance to experiment a little bit with your calculators, let's see what these answers to these questions should be. All of these polar graphs are the shape of a circle. In the equations r equal a cosine theta and r equal a sine theta, the absolute value of a is the diameter of the circle. The graph of r equal a cosine theta will lie on the positive x-axis, positive x-axis if a is greater than 0, and the negative x-axis if a is less than 0. If it is the graph of r equal a sine theta, it will lie on the positive y-axis if a is greater than 0, and the negative y-axis if a is less than 0. All right, so let's write some of these equations for these specific situations. We want the equation of a circle centered at the origin with a radius of length 6. So that would be similar to our original problem where we were just graphing r is equal to a specific value, and there r was equal to the radius, so r is equal to 6. If we want the equation of a circle lying on the negative y-axis with a radius of 4, well, we would have to use a sine function, and not y, but r. r is equal to, and 4 is the radius, so 8 is the diameter, and it needs to be on the negative y-axis, so we need that to be negative 8. And lastly, we need to write the equation of a line with a slope of -1, which passes through the origin. So if you can imagine this line being drawn in, except thinking about it in terms of the directed angle, it would be a directed angle of 3 pi over 4, or any angle that is coterminal with that, or any angle that is 180 degrees opposite that.